All right, hey guys, happy Thursday once again to you. It's Mr. D here. Today we're going to be starting a new unit. It is Unit 6. This unit's going to be introducing some of the concepts that you'll be using in pre-calculus next year if you decide to take that class, as well as reviewing some of the older concepts from Algebra 2 and geometry. So our learning targets for today are I can use the Pythagorean theorem to find coordinates of points on a circle centered at the origin, and I understand that a periodic function is one with outputs that repeat at regular intervals. Don't mind the fact that it's written twice there. So we'll take a look at our first task here. Task 1 is called Around and Around. It says a ladybug lands on the end of a clock's second hand when the hand is pointing straight up. The second hand is 1 foot long, and when it rotates and points directly to the right, the ladybug is 10 feet off the ground. Our first question is how far above the ground is the ladybug after 0, 30, 45, and 60 seconds have passed? So I think for this one, it can be helpful for us to draw a diagram. So I'm just going to scroll to the end here where I have some space to draw, and we'll see if we can get a good one going on. So we have this clock. We know that the second hand is 1 foot long, so I'm just going to go ahead and label that on my diagram here. This is 1 foot. And it also tells us that when the hand is pointing directly to the right, that our distance from the ground is 10 feet. So this distance will be 10 feet. So our first question was, how far is the ladybug after 0 seconds? So that would be right when it lands on the second hand right here. All we have to do to find that distance is add our 10 feet off the ground to the 1 feet length that the second hand has, and we get our total answer of 11 feet after 0 seconds. Next, it wants to know after 30 seconds. So once 30 seconds have passed, the second hand is going to be pointing straight down instead. So 15 seconds would bring us to the 10 feet height, and then we would have another 1 foot that this time we have to subtract since we're 1 feet below when it's pointing straight to the right. So our distance when we're pointing directly down would be 9 feet. Next, it wants to know what the height is after 45 seconds have passed. So 45 seconds is going to be the same height as 15 seconds when it's pointing directly to the right. We're just pointing to the left instead, but our height hasn't changed. So we'll still be 10 feet. And then after 60 seconds, we're just back where we started, right? We're pointing straight up again. So we'll still be at 11 feet, just like we were at 0 seconds. And that does it for the first problem. So now we'll go ahead and take a look at number 2 together. So this one wants to know how far above the ground the ladybug is after 10, 20, and 40 seconds. So again, I'm going to go ahead and draw a diagram here. We know that when the hand is pointed directly right, we're at 10 feet. So I'm just going to label this as 10. And we know the top is 11 and the bottom is 9. So after 10 seconds, we're going to be right about here on the clock. Sorry, I messed up that drawing a little bit. Let me try that a little bit better. There we go. So this would be like where the 1 o'clock is, the 2 o'clock is, and then the 3 would be down here. So 2 o'clock is right at the 10-second mark. So we know that that's going to be someplace between 10 and 11 feet, right? It's going to be a little bit closer to the 3 than it is going to be to the 12 on the clock. So as far as estimations go, I think that we're good to say maybe about 10.3 feet. About 10 and a third, about a third of the way to the top. Okay, so after 20 seconds, the second hand will be pointing at the 4 on the clock, right? Right about there. So now we're going to be between 9 and 10, but a little bit closer to 10. So I'm willing to say about 9.6 feet. That's about 9 2/3. 9.7 you could say as well. Again, for this one, it's just estimation, so we don't have to worry about being super precise, just as long as we get something close. And then 40 seconds, that's going to be where the clock is at 8, right? Right about here. So we'll be at the exact same height. If I were to draw a line here, we can see that the height is the same between the two of them. So the difference between 20 and 40 seconds is just that the hand is going to be pointing to the left instead of the right, but the height itself won't actually change. So I can put the same exact guess for after 40 seconds. And that will do it for number 2. So next up, we're going to take a look at number 3. That one says, if the ladybug stays on the second hand, describe how its distance from the ground will change over the next minute. What about the minute after that? So we can imagine, let me see if I can draw a little graph here that'll make this concept a little more clear. We can imagine that 11 feet is the ladybug's starting point, right? So I'm going to draw this nice little graph here. I'm going to call this top part 11 feet off the ground, the middle one 10 feet off the ground, and the bottom one 9 feet off the ground. We know that the ladybug starts at 11 feet, so let me change colors, and I'll go ahead and put a little dot on my graph there at the 11-foot mark. So that is our ladybug's starting position. We also know that after 15 seconds, we're at 10. After 30 seconds, we're at 9. After 45 seconds, we're back at 10 feet off the ground. And after 1 full minute, we're back where we started at 11 feet off the ground. So the motion of the ladybug in terms of its height off the ground is actually going to be this repetitive function where it repeats back on itself after every minute. It starts at 11 feet, it lowers in height until it gets to 9 feet after 30 seconds, and then it starts increasing in height again until it reaches 11 feet. And then that motion is just going to repeat for every minute that passes. So if I wanted to describe this in words, I could say something along the lines of, its height repeats itself every minute. And then I could be a little more specific by saying it starts at 11 feet off the ground when no time has passed. Decreases in height until it reaches 9 feet, then increases until 11 feet again. So the main idea is just that this height is going to be repeating back on itself. So we start off at the maximum height, we start decreasing in height until we reach the minimum, and then we increase once again until we get back to our original maximum of 11 feet. So that'll do it for number 3. Number 4 says, at exactly 3:15, the ladybug flies from the second hand to the minute hand, which is 9 inches long. How far off the ground is the ladybug now? So let's see if we can go ahead and refer back to our original diagram. I'll erase some of this and make some modifications to it. So I'm going to start by drawing the second and the minute hand on the clock here. We know that the time is 3:15. So at 3:15, both the second hand and the minute hand are going to be pointing directly to the right. I'm going to use purple for my second hand. So it'll be the same color as the rest of the clock. And then I'll use this pink shade for my minute hand. So this is 315. So I'm going to use this green color to indicate where the ladybug was. So at exactly this time, the ladybug was right here on the minute hand, and then it flies over onto the second hand. It wants to know how high the ladybug is. Well, we know that this height is already 10 feet from earlier in our problem. The fact that it's flying over to the minute hand instead of the second hand isn't going to change anything because the minute and the second hand are in the exact same position. Sure, the minute hand is a little bit shorter than the second hand here, but the height from the ground is not going to change as a result of it flying just closer to the center of the clock. So we can go back and answer our question. How far off the ground is the ladybug now? I will say still 10 feet since the minute hand and the second hand are both pointing directly right at 315. And now it says, at what time will the ladybug be at that height again if it stays on the minute hand? Be prepared to explain your reasoning. Well, let's think about it. We'll go back to our diagram here. We need to get back to 15 feet. So I'll use purple once again, or pink rather, for my minute hand. Our minute hand is going to decrease in height for a little while as time passes, and then start increasing in height once it passes the 6 on the clock, until it gets to about here. At this point, it'll be pointing directly to the left instead of the right, and still be at that same height of 10 feet. Kind of looks like a Pokeball, doesn't it? So going back to answer our question, at what time will the ladybug be at that height again? Well, when the minute hand is pointing directly to the right, it will be 3:45. I'll say, since then, the minute hand will be pointing directly left, but still at the same height. So with that first task taken care of, we've been dealing with this clock where the motion is moving in a regular interval. We have some definitions that can help us conceptualize this next. The first definition says the length of an interval at which a periodic function repeats itself is called the, and we refer to that in the math world as the period. A function f has period p if f of x plus p equals f of x for all inputs x. So all that second part is saying there is that if a function's output repeats itself every time you add some constant value, p, to the function, then the function has a period equal to that value that you were adding, p in this case. So they give us this nice little diagram here. As we can see, this function is just going to repeat itself. Let me see if I can go ahead and sketch on top of that to maybe extend it out a little bit further. So this function is just like a wave that is going to keep repeating back on itself over and over again. So this amount of time right here, or this distance, I guess I should say right here, this p, is the period. We can see that right here and right here, the function has the exact same value, and all the function is doing in between is the same shape that's going to be repeating over and over and over again. So we could draw our different periods in different colors. We'll start with maybe yellow there, and then green on this one. And then I'll use blue for the next one. And then a last one with maybe orange here. But the function is actually just repeating itself over and over every p units that pass. So let's take a look at our second definition here. So this second definition is kind of restating what we knew for the first one. It says a function whose values repeat at regular intervals is called a periodic function. If f is a periodic function, then there is a number called p, such that f of x plus p is equal to f of x for all inputs x. So again, that's just going back and saying what we said for the first definition again. We've got this type of function that repeats itself called a periodic function. And the amount of time or distance or whatever our unit on the x-axis is here that it takes for that function to repeat itself is called the period. So with those definitions in mind, we'll take a look at the second task. This one's called Where is the Point? So first thing it wants us to do is find the radius of this circle. It gives us a circle, and then it marks this point on the edge of the circle as -5, 12. So there's some tools that we know that we could use to figure out what the radius of this circle is, but we'll have to think back to geometry for it. Hopefully we all remember the Pythagorean theorem. That, once again, for anyone who doesn't remember it, is, let me get a better color to write with here. We'll use purple, I suppose. A squared, hey, that's not purple, plus b squared equals c squared. So with that formula in mind, we can draw a right triangle out of this circle here and use our Pythagorean theorem to find what the length of the radius is. We know that this height right here is 12 units because the y value of our point is 12. So I'm just going to draw a line from there to the center of the circle and call this height 12. We also know that because the x-coordinate of our point is -5, that the distance between here and here is 5 units. We could also label that 5 up top if it makes it a little bit more clear. And then I'm going to go ahead and draw a line from the center of the circle directly to the point. So this line is going to be the radius of our circle. It also happens to be the hypotenuse of this right triangle. So we can use the Pythagorean theorem here to find what this distance is. Pythagorean theorem says that the legs squared and added together have to equal the square of the hypotenuse. So my first leg is 5, so 5 squared, plus my second leg is 12, 12 squared, has to equal my radius squared. Now all I'm going to do is simplify my left-hand side, take the square root of both sides to find what the radius is. So 5 squared is 25. 12 squared is 144. Equals r squared. 25 plus 144 is 169. And to get rid of this squared over here, I'm going to go ahead and take the square root of both sides of the equation. Now, normally I know when we take the square root of both sides, we have to include a plus or minus sign on one side. However, because we're dealing with a distance here, there's no such thing as a negative distance. So we don't need to actually include this sign in this particular case because we're dealing with distance. Any other time, if a negative was possible, we would need the plus or minus sign to get the correct answer. In this case, we don't need it. So the square root of 169 is just 13. On my right-hand side, we have a square and a square root. Those are inverse operations of each other. So the square root of r squared is just going to be r. So that means our r, the radius of our circle, will be 13. And I'll circle that since it's my answer. Next up, number 2. If Q has a y-coordinate of -4, what is the x-coordinate? So in this case, they're telling us that this distance here has a length of 5. They also tell us that Q has a y-coordinate of -4. So I'm going to write an ordered pair with x because we still don't know what the x-coordinate is, and -4. So that means that this distance, since we know that the x-axis has a height of 0 units, is a distance of -4. We don't know what this length is, so I'm going to call it my x. And then maybe just so that it's a little bit easier to see, I'm going to scribble out this 5 here and write it over here so that we don't get confused about what side that 5 is talking about. So again, I'm just going to use the Pythagorean theorem. A squared plus b squared equals c squared. Here we already know what our c is. Our c is always the length of the hypotenuse, and in this case, our right triangle's hypotenuse has length 5. So I'm going to replace my c with a 5. We also know that one of our legs has a length of 4 units. Doesn't matter that it's negative because we're going to be squaring it in the Pythagorean theorem anyways. Also, distance can't be negative. If you want, you could write -4 there. When you square it, you would still get 16. I'm just going to write +4. And then our other side is the unknown x, so I'll just leave that as x for now. So our equation setup is x squared plus 4 squared equals 5 squared. Let's see if we can solve that. So 4 squared is just 16. 5 squared is 25. So we have x squared plus 16 equals 25. I'm going to go ahead and erase this to make a bit of space down here. I want to solve for x, so I'm going to have to subtract 16 from both sides to get x by itself. So the positive and -16 cancel each other out. We'll have x squared is equal to 9. To undo the squared, we're going to have to take the square root of both sides. Again, normally here we would have to include a plus or minus, but we're dealing with distance, and we know that distance cannot be negative. So all we need to look at is the positive square root. The square root of 9 is 3. So that will be our answer here. So next we'll take a look at number 3. If B has a y-coordinate of 4, what is the x-coordinate? So again, they're telling us the hypotenuse of the right triangle we'll have to create here. I'm going to go ahead and draw the rest of my triangle. So it's telling us that the y-coordinate of B is 4. That means that we'll have an ordered pair of x positive 4 here. So the y-coordinate always tells us the height. That means that this distance is 4 units. We don't know what the x-coordinate is, so I'm just going to call that x for now. And again, we're going to plug this into the Pythagorean theorem. So our unknown side squared plus our leg with length 4 squared has to equal our hypotenuse squared. This looks suspiciously similar to the last problem. I'll continue solving from here. X squared plus 16 is equal to 25. Subtract 16 from both sides. X squared equals 9. Take the square root of both sides to cancel out our squared. And x is equal to 3. Again, we don't have to include the plus or minus because we're finding a distance, and there's no such thing as a negative distance. So our answer for this problem is 3. And our last question for this task, number 4, a circle centered at 0, 0 has a radius of 10. Point S on the circle has an x-coordinate of 6. What is the y-coordinate of S? Explain or show our reasoning. So in this case, they didn't actually give us a diagram, so I'm going to go ahead and draw it. So it tells us that our circle is centered at 0, 0. So this will be the center of our circle. We have a radius of 10. So that means we're out here at 10 10, 10 in every direction. And then it says that point S has an x coordinate of 6. So it'll be maybe right about here, a little bit over halfway. So this will be our right triangle that we have to look at to solve this problem. This is point S, which is located at 6, and then some y value. We need to find what that y value is. So I'm going to go ahead and plug in the Pythagorean theorem just like I have been in the past. We know that this distance is 10 because the radius of our circle is 10. We also know that this distance is 6 because it was given to us as the x coordinate. So our unknown value here is this height, which I'm going to call y. So 6 squared plus y squared has to equal my hypotenuse squared, and the hypotenuse in this case is 10. So we've got 36 plus y squared is equal to 10 squared, which is 100. I'll subtract 36 from both sides. So we end up with y squared is equal to, what's 100 minus 36? That would be 70 minus 6 is 64. Just continuing a little bit over to the right since I'm out of room on the bottom of the page there. So we have, sorry about that, guys, computer acting up. So we have y squared equal to 64. We're going to have to take the square root of both sides once again to find our answer. And once we do that, we just get y is equal to the square root of 64 is 8. Remember, the way we find square roots is by looking for a number that multiplies by itself to give us what we started with. So we know that 8 times 8 equals 64, therefore the square root of 64 is 8. So our height then is 8 for our answer. So moving on to task 3 here. This one is going to be a bit of a review of the trigonometry stuff that you learned in geometry. It gives us a right triangle, and it just wants us to find the cosine, the sine, and the tangent of angle A. So let's start by recalling what the formulas for each of those are. Remember that the formula for sine is the opposite side from the angle divided by the hypotenuse. Oops, that's not a P. The cosine is defined by the adjacent sine divided by the hypotenuse. And tangent is defined as the opposite side divided by the adjacent side. So we already know that angle A is this angle right here. All we have to do to find what the sine, cosine, and tangent are is divide each of the corresponding sides by each other. So I'll start with cosine since that's the first one it asks us for. So the cosine of A is going to be equal to, all we have to do for cosine is divide the adjacent side by the hypotenuse. Our adjacent side is going to be the 15 down here. Our hypotenuse is always opposite from the right angle, so that'll be the 17. So it'll just be 15/17. Sine of A is going to be the opposite side divided by the hypotenuse. So our opposite side from A is all the way over here at this 8, divided by hypotenuse is still 17, so it'll just be 8/17. For the tangent, we look at the opposite side divided by the adjacent, so that'll just be 8/15. Easy as that, and we are done with number 1. Number 2, sketch a triangle DEF where sine D is equal to cosine D and E is a right angle. What is the value of tangent D for this triangle? Explain how you know. Okay, so I'm going to start by just drawing the triangle that it's asking us for. So it wants E to be a right angle. So we'll call this side, or this corner rather, E, so that we can have a right angle there. So we'll call the far side D, and then our top side up here will be F. It wants sine of D to equal cosine D. So we know that we're always going to be dividing by the hypotenuse. I'm going to call this hypotenuse length E for now. So in order for the sine to equal the cosine, that means that the opposite and the adjacent have to have the exact same length, right? Because we know that we're going to be dividing something by the hypotenuse. So I'll put sine of D is equal to cosine D, which is equal to something divided by that hypotenuse length, which is E. So in other words, it doesn't matter what length we choose for our adjacent and our opposite side. We just need those to be the same, because when they're the same, the sine will equal the cosine. So I'm just going to call it some number x. It doesn't really matter what x is equal to, because as long as they're the same, sine of D and cosine D will be equal. What is the value of tangent D for this triangle? Well, we know that tangent is equal to the opposite divided by the adjacent. Here our opposite side is x, and our adjacent side is also x. So what we have is some number divided by itself. And we know that any number divided by itself is equal to 1. So when the opposite and the adjacent sides are equal to each other, the tangent will always be 1. Let's take a look at our third question here. So it says, if the coordinates of point I are 9, 12, what is the value of cosine G, sine G, and tangent G for the triangle GHI? Explain or show your reasoning. So we know that the x value of our point is 12 because it's directly above h here. We know that because of the right angle here. Sorry, the x value is 9, I should say, not 12. I misspoke. So I'm going to go ahead and label this as 9 and then something. We don't know what that height is yet. So before we can talk about what the sine, the cosine, and the tangent are, we're going to need to know what all of the side lengths here are. We know that this side length is 9 because we have to go out 9 units to get to this point. Oops. So our next step is going to be to find out what this height is here. In other words, what is the value of y? Thankfully, it tells us in the prompt that the coordinates of point I are 9, 12. So I can go back and rewrite this as 9, 12. Because we're moving straight up, that means that this distance is also 12. So we can use the Pythagorean theorem then to find what our missing side length is here. So our hypotenuse will be equal to 9 squared plus 12 squared from the Pythagorean theorem. And I'm just going to call it hypotenuse for now. HYP, short for hypotenuse. So 9 squared gives us 81. 12 squared gives us 144. And when we add those together, we get the square of the hypotenuse. So what is 81 plus 144? I believe that should be equal to 225. So 225 equals the square of the hypotenuse. And then we take the square root of both sides to undo the squared. Just like before, we're talking about a distance here, the length of this side of the triangle. So we can't have a negative. We don't have to include the plus or minus. So we'll just have 25, which is the square root. Oh, sorry, I lied. Not 25. 15, which is the square root of 225. So my length here will be 15. So now we know all of our sides. Our first leg has length 9, our second leg has length 12, and our hypotenuse has a length of 15. So we want to find out what the value of cos G, sine G, and tangent G are. We know that cosine is the adjacent over the hypotenuse. So cosine G will be equal to, our adjacent side is this one here, this 9. And our hypotenuse is 15. So 9/15 will be our answer. Next, we'll take a look at the sine. For sine, we have to look at the opposite side. So our opposite side is 12 divided by our hypotenuse, which is 15. And tangent of G, we have to do the opposite side divided by the adjacent side. We get 12/9. We can actually simplify a little bit more here. Know that 12 and 9 both have a factor of 3. So if I divide 12 by 3 and 9 by 3, I get 4/3 as a more simplified answer. Actually, looking back, I can simplify all of these, can't I? They all have factors of 3. So I'll write 12 over 15 as 4 over 5, since 3 goes into 12 4 times and 15 5 times. I'll write 9 over 15 as 3 over 5. These are our more simplified versions. That takes care of task 3, so we'll take a look at our last task for the day. Task 4, shrinking triangles. So what are cosine D, sine D, and tangent D for our first problem? Explain how we know. Okay, well, we'll do this with the Pythagorean theorem, just like we've been doing the last couple of them. So we know that our first leg has a length of 12, since it goes out to 12 on the x-axis after starting at 0. We can see that our second leg has a length of 5, since it goes up to 5 on the y-axis here. And we don't yet know what our hypotenuse's length is, so we'll use the Pythagorean theorem to find that. 5 squared plus 12 squared equals, this time I'll use h for my hypotenuse. So h squared. Squaring both 5 and 12 gives me 25 and 144. And then when we add 25 and 144 together, we get 169. So to undo this squared on the right-hand side, again, we will take a square root, the inverse operation of squared. So the square root of h squared is just going to be equal to h. We don't have to include the plus or minus because we're dealing with distance. And the square root of 169 is 13. So now we have our angle D already labeled for us here. Let's just go ahead and find out what the cosine, the sine, and the tangent of D are equal to. So cosine of D will be equal to, the adjacent side here is 12, the hypotenuse is 13. We divide those two together. 12/13 is our answer. Sine of D, now we have to look at the opposite side on the hypotenuse. Our opposite is 5, our hypotenuse is 12, so 5/12 will be our answer. And for tangent, we must look at the opposite side divided by the adjacent, so 5/12 will be our answer. So now we'll move on to number 2. It gives us a triangle similar to DEF. So in case you forgot the definition of a similar triangle, I know it was a while ago in geometry that you last saw that. All that means is that all of the angles in the triangle are the same. However, the distance is different. So in this case, instead of having side lengths of 12 and 5, we've got leg lengths of 36 and 15. So all the lengths in this triangle have been multiplied by 3. So what is the scale factor from DEF to D prime, E prime, F prime? Explain how we know. By the way, whenever I see these apostrophes, I just pronounce them as prime. You may or may not have heard some of your other math teachers do that. If you hear me talking about primes, all I mean is that's how I pronounce the apostrophe. So I'm going to say the scale factor is 3 since the legs are both 3 times as long as they are in DEF. So again, all I did to figure out that 3 number is I saw that my original triangle had a side length of 12, my new one had a side length of 36, and 12 times 3 gives me 36. For the vertical side, I saw that it had a length of 5. This one has a length of 15, going up to 15 on the y-axis there, and 5 times 3 gives me the 15. So since multiplying by 3 gives me the new side lengths, I know that the scale factor is 3. So what are cosine of d primed, sine of d primed, and tangent of d primed? Well, we could use the Pythagorean theorem once again to find what this hypotenuse is in our new triangle. However, we already know what the scale factor is, so we can also just multiply what our old hypotenuse was by 3. I like that a little bit better. So I'm just going to go ahead and multiply my old hypotenuse, which was 13, by 3, and that gives me 39. If you want, you can check that with the Pythagorean theorem. Feel free to pause the video and do that to see that even if we plugged in our new side lengths into the Pythagorean theorem, we would still end up getting that same length of 39. So what are cosine of d primed, sine of d primed, and tangent of d primed? Well, let's just go ahead and use our trigonometric formulas to find that. We know that the cosine is the adjacent side divided by the hypotenuse. How do I get rid of this guy? There we go. Our adjacent side here is 36 divided by 39. And I know that 3 divides into both of these numbers evenly. 3 goes into 36 12 times, because 12 times 3 equals 36. And it goes into 39 13 times, since 13 times 3 equals 39. So I can simplify that as 12 over 13. And what do you know? Oh, I forgot the primed on this one. Let me go ahead and put that in there so we don't get confused. There we go. The cosine of d just happens to be equal to the cosine of d primed. Let's see if that holds true in all of our cases. Let's find what the sine of d primed is. For sine, we have to look at the opposite divided by the adjacent. So it'll be 15 divided by 39. Again, both 15 and 39 are multiples of 3. 3 times 5 gives me 15. And 3 times 13 gives me 39. And we can see that, oh, I just realized, back on this one, I made a mistake. Apologies, that should be a 13. So with that correction, we can see that sine of d primed is indeed equal to sine of d. And lastly, we'll take a look at the tangent. For the tangent, we have to look at the opposite side divided by the adjacent. So we'll have 15 for our opposite divided by our adjacent side of 36. Again, 15 and 36 are both multiples of 3. If I divide 15 and 36 by 3, I get 5 and 12 respectively. So 5/12, which happens to equal the tangent of d. So we can make an observation here. In similar triangles, again, similar just means having the same angle measurements, even if the lengths of the sides are different. In similar triangles, the sine, cosine, and tangent are equal. Take a look at number 3 now. Here's another triangle similar to DEF. Label the triangle D double primed, E double primed, F double primed. So we'll start by labeling it. D double primed, E double primed, and F double primed. So first it wants us to find what are the coordinates of F double primed. Oh, sorry, I skipped a question. Part B. First thing it actually wants to know is what is the scale factor from DEF to D double primed, E double primed, F double primed? Well, let's take a look. We can see that on our hypotenuse here, we have a length labeled of 1. On our original triangle, the hypotenuse had a length of 13. So that means this hypotenuse is 1/13 the length of our original triangle's hypotenuse. So because this side has exactly 1/13 the length of the corresponding side, the scale factor is 1/13. My explanation there is since the hypotenuse of D double prime, E double prime, F double prime has 1/13 the length of DEF's hypotenuse. So what are the coordinates of F double primed? Explain how we know. Well, if we take a look at DEF, we can see that F has a coordinate of, or coordinates of, I guess I should say, 12, 5. So if I multiply those coordinates, since we're starting at the origin here, by 1/13, we should be able to get the coordinates of F double primed. Just multiply the scale factor by what the old coordinates are. That works as long as we're starting at the origin, which we are here. If we weren't starting at the origin, we could still find the lengths of these sides by multiplying the length by the scale factor, the old length by the scale factor. But here we don't even have to bother with that since we're starting at the origin. So I'll start with finding the x coordinate. I'm just going to take my old x coordinate, which was, I believe, 12. Yep. Times my scale factor, which is 1/13. And 12 times 1/13 is just going to be 12/13. For my y coordinate, I'll do the same thing. Take my old y coordinate, which was 5, multiply that by my scale factor of 1/13. And I'll get 5/13. The coordinates of F double primed will just be the ordered pair 12/13. Actually, let me hand draw that one out. I think it might be a little bit clearer to not have the backslash. You can actually see it with the fraction bar. So 12/13 and 5/13. And that'll be our answer for that one. Next up, it wants to know what are cosine of d double primed, sine of d double primed, and tangent of d double primed. Well, we know what the coordinates of f are, so we can label what these distances are. So this distance will be 12/15ths, and this distance will be 5/15ths. Sorry, 13ths, not 15ths. My bad. There we go. So if I want to go ahead and take the cosine, sine, and tangent, all I need to do is know what all of my lengths are. So cosine is the opposite side divided by the adjacent side. Sorry, the opposite side divided. Let me try that one more time. Adjacent side divided by the hypotenuse. There we go. Got it right that time. Third time's the charm, right? So cosine d double primed will be equal to the adjacent side is 12/13ths. Divided by the hypotenuse, which is 1. But anything divided by 1 is just itself, so 12/13ths divided by 1 is still 12/13ths. Next, we'll take a look at the sine of d double primed. So for sine, we have to look at the opposite side divided by the hypotenuse. Our opposite side is this 5/13 right here. So we'll have 5/13ths divided by the hypotenuse is still just 1. And anything divided by 1 is itself. So still 5/13. And just to keep it from getting too confusing while we get squished into the bottom there, I'm going to switch to pink instead of purple for the tangent. Tangent of d double primed. Now we have to look at the opposite side divided by the adjacent. So we'll have 5/13ths divided by 12/13ths. And remember, whenever we have an improper fraction like this, where we have a fraction that also has smaller fractions in the numerator and the denominator, we can evaluate that by pulling the denominator out and flipping it, so multiplying by the reciprocal. So this is going to be the same thing as 5/13 times 13/12. When we multiply fractions, we go straight across. So 5 times 13 gives me 65, I believe. 13 times 12, well, let's see. 12 times 12 is 144. We need one more 12 to make it 13. So 144 plus 12 would be 156, I believe. And when we simplify that, we just get 5/12. I'm not 100% confident in my work here, so let me check it real quick. Yeah, this ends up being true because 13 divides into 65 5 times and 156 12 times. So we did it right. So we have our answers. For cosine of d double primed, we got 12/13. For sine of d double primed, we got 5/13. And for tangent of d double primed, we got 5/12. And that concludes it for today's lesson. Next up, you have the summaries. Make sure you go ahead and read through those in case there's anything that I did not explain correctly. Hopefully everything I said makes sense, but if it didn't, feel free to email me with any questions. My email is just my name, tylerdewhurst@gmail.com. Also, remember that Mr. Cardenas hosts regular tutoring sessions and office hours, so definitely take advantage of those. Shoot him an email in case you forgot when they are, Office hours are by appointment, but you can set one up with him. Tutoring, you can just show up to and have a grand old time learning math. I will see you guys again in 1 week. Stay safe out there. And we're almost to the end of the year now. I know this distance learning stuff is weird, but hang in there. It'll be over before you know it. Enjoy the rest of your week, guys.